Most AI tutorials skip the math or drown you in equations. We're going to do something different. In 10 minutes, you'll understand the only math that actually matters for AI, and we'll do it visually. Welcome to Episode 4, The Math Behind AI, Made Simple. I promiza no escaritaxbooks. Just the essentials explained visually. AI math comes down to 3 pillars. First, linear algebra. This is how we represent data. Vectors, matrices, tensors. Second, calculus. This is how the model learns. Specifically, derivatives and gradients. Third, probability. This is how models handle uncertainty. Distributions and Bayes' theorem. That's it. Master these 3, and you understand the math behind every AI system on the planet. Let's start with linear algebra. Everything in AI is a number. A pixel is a number. A word is a vector of numbers. An image is a matrix of numbers. A video is a tensor, a multidimensional array. When you hear the model processes the input, it's really just doing math on arrays of numbers. Vectors are 1D arrays. Matrices are 2D, and tensors are any dimension. The most fundamental operation in AI is matrix multiplication. When data flows through a neural network, each layer multiplies the input vector by a weight matrix. Here's a simple example. A 2x3 weight matrix times a 3-element input vector give a 2-element output. Every single layer of every neural network does this operation millions of times. Now for calculus, specifically gradient descent. The model has a loss function that measures its error. The derivative of the loss tells us the direction and rate of change. The gradient is just the derivative in multiple dimensions. To minimize error, we move in the opposite direction of the gradient. The learning rate alpha controls how big each step is. Too big, you overshoot. Too small, you're too slow. The learning rate is one of the most important hyperparameters. If it's too large, the model overshoots the minimum and bounces around chaotically. If it's too small, training takes forever and might get stuck in a local minimum. Finding the right balance is both art and science. Finally, probability. AI models don't give absolute answers. They give probabilities. A classifier might say 85% cat, 10% dog, 5% rabbit. Bayes' theorem is the foundation. It tells us how to update our beliefs based on new evidence. The posterior probability equals the likelihood times the prior, divided by the evidence. This is how spam filters, medical diagnosis, and recommendation systems all work under the hood. One more key concept: activation functions. After each layer does its matrix multiplication, we pass the result through a nonlinear activation function. Without this, the entire network would collapse to a single linear function, no matter how many layers. The sigmoid squashes values between 0 and 1. ReLU sets negatives to 0. Softmax converts values into a probability distribution. These tiny functions are what give neural networks their power. Let's put it all together. Data is represented as tensors using linear algebra. It flows through the model via matrix multiplications. Activation functions add nonlinearity. The loss function measures error using probability. And gradient descent uses calculus to minimize that error. That's the entire mathematical backbone of AI in 5 steps. You just learned the math behind AI. Linear algebra for data, calculus for learning, and probability for uncertainty. In the next episode, we'll trace how data flows through an entire AI pipeline from collection to deployment. This is going to be the ultimate reference diagram. Subscribe, and I'll see you there.